5,000 meters below the surface, in the pitch black, a mysterious source of oxygen has just been discovered.
A haunting observation in the blackest depths of the Pacific shattered what science had taken for granted. In total darkness, sealed off from air and light, oxygen was mysteriously rising. As sensors blinked and readings piled up, a quiet truth emerged. The ocean floor might be breathing without life, and without the sun. It started with a single anomaly in the Clarion Clipperton Zone, an error, or so they thought. But the more they checked, the more impossible it became to dismiss. One impossible reading. In 2024, marine ecologist Andrew Sweetman was conducting routine oxygen monitoring in one of the most desolate places on Earth, the Clarion Clipperton Zone, a vast stretch of deep-sea plain between Hawaii and Mexico. His instruments were placed over 13,000 feet below the surface, where the cold is constant, sunlight has never reached, and the crushing pressure would collapse a human body in seconds. The mission was simple: measure how much oxygen remained as deep-sea life slowly consumed it. After all, that's what every previous study had shown. The deeper you go, the less oxygen remains. But this time, something was off. Oxygen levels weren't dropping. They were rising. Sweetman initially dismissed it as a technical failure. He recalibrated the sensors, swapped out instruments, even used alternative methods based on entirely different scientific principles. But the pattern persisted. Inside the sealed measurement chambers, resting silently on the seafloor, oxygen was not being consumed. It was being created. The readings defied logic. No photosynthesis could occur here. There was no sunlight, no plants, no known chemical process that should result in rising oxygen under such conditions. Yet, Sweetman's data kept insisting otherwise. Each experiment repeated the same story. A quiet but insistent pulse of oxygen forming in one of the most inhospitable places on Earth. And if the data was right, it meant something extraordinary. A process was unfolding in the deep that no one had ever observed, one that might rewrite how we understand life itself. The abyss unfolds. The Clarion Clipperton Zone spans a patch of Pacific seafloor larger than the continental United States. At a glance, it appears barren, an endless desert of fine sediment, soft clay, and perpetual darkness. But scattered across this abyss are strange potato-sized rocks, polymetallic nodules. Formed over millions of years, each is a layered mosaic of manganese, nickel, cobalt, and copper. They accrete atom by atom, growing slower than human fingernails, like mineral time capsules embedded in mud. To an industrial eye, they represent wealth, rare metals critical for electric vehicles, batteries, and solar panels. But to the life forms of the deep, they are so much more. In a world without hard surfaces, the nodules are islands of stability. Fragile corals anchor to them. Ghostly white anemones drift above their surface. Barbie pink sea cucumbers shuffle across them on gelatinous feet. Dumbo octopuses and ancient glass sponges, some older than medieval castles, cling to the stillness around them. And many of these organisms exist nowhere else. Over 90% of the species found here are unknown to science, some restricted to patches of seafloor no larger than a football field. This ecosystem had evolved around the nodules, shaped by their structure, chemistry, and permanence. But until now, no one had imagined that these unassuming rocks might be doing more than hosting life. Deep in the sediment, Sweetman's sensors hinted at something else, something electric, hidden inside the nodules themselves. The rocks, it seemed, were not passive relics. They might be active engines. Oxygen without light. Back in the lab, Sweetman and his colleague Franz Geiger began dismantling the mystery, one layer at a time. They examined the polymetallic nodules more closely and found something astonishing. The rocks were generating electrical voltage, not in theory, but in practice. Their layered metal composition, manganese wrapped around nickel and cobalt, acted like the anode and cathode of a battery. In some cases, a single nodule produced nearly 0.95 volts, just shy of the power output of a household AA battery. This wasn't a trick of instrumentation. The nodules, long dismissed as geological curiosities, were functioning as natural batteries. and when multiple nodules clustered together across the seafloor, the voltage increased, mimicking batteries wired in series. Sweetman and Geiger proposed a bold hypothesis. The electric currents produced by these nodules were splitting seawater molecules through electrolysis, releasing oxygen in the process, entirely without sunlight, without photosynthesis, without life. It was a revelation that challenged the origin story of breathable Earth. For decades, scientists believed that cyanobacteria were the first organisms to produce oxygen, beginning around 2.7 billion years ago and transforming the planet's atmosphere. But this discovery hinted at something even older. If metal-rich stones had been quietly producing oxygen through electrochemical reactions long before cyanobacteria ever existed, then life may have emerged not because of biology, but alongside geology. When Sweetman's findings were published in Nature Geoscience in mid-2024, the scientific community stirred. Some researchers hailed it as paradigm shifting. Others warned against overreach. But one thing was clear. If oxygen can be created in darkness on a world like ours, then perhaps it can emerge anywhere, whether beneath the sea or beneath the ice of distant moons. Beyond the nodules. As Sweetman's research rippled through the scientific world, another study, published just a year earlier by a team at the University of Tokyo, offered a surprising parallel. In a different stretch of the seafloor, researchers had been studying volcanic basalt, the black rock left behind by ancient undersea eruptions. These basalts weren't just inert remnants of geological time. When submerged in seawater, they were generating their own electrical currents. Unlike polymetallic nodules, these basaltic rocks formed geoelectric fields through a different mechanism, redox reactions at their surface, driven by gradients in dissolved minerals and temperature. The fields were subtle but measurable, and most importantly, they created just enough energy to sustain microbial life, without any access to light. Some scientists now believe that these geoelectric fields may mimic the conditions under which the first life on Earth arose, powering the metabolism of primitive organisms in a sunless world. Taken together, the findings suggested something even more profound, that the deep ocean doesn't just host a single source of energy outside the biosphere, it may contain many. Across different geological environments, from metal-rich nodules to volcanic basalt, Earth's crust seems to quietly produce energy and even oxygen through purely physical processes. No sunlight required, no biology involved, just chemistry, pressure, and time. In a world where we once believed oxygen could only emerge from photosynthesis, the revelation that multiple mineral systems may independently generate it reframes everything. The ocean floor isn't just alive, it may be part of the machinery that made life possible. Science versus industry. For mining companies, polymetallic nodules represent a long-awaited solution to the green energy race, rich in metals crucial for electric vehicles, solar panels, and rechargeable batteries. The nodules could supply global demand for decades. 16 firms currently hold exploration licenses in the Clarion Clipperton Zone, and full-scale extraction operations are being designed now. Massive underwater vacuum systems that will scrape the seabed clean and haul the nodules to the surface by the ton. But if these nodules aren't just metallic lumps, if they're producing oxygen in one of Earth's most hostile ecosystems, then removing them could suffocate the very life forms that evolved around them, and that has triggered a fierce and growing backlash. Environmental organizations, marine biologists, and policymakers are raising urgent questions. What else are these nodules doing that we don't yet understand? What invisible roles do they play in carbon cycles, microbial networks, and the chemistry of the abyss? Some nations, including Costa Rica and Panama, have already called for moratoriums, citing Sweetman's research and negotiations before the International Seabed Authority. Meanwhile, criticism of the dark oxygen hypothesis has intensified. Skeptics argue the voltage is too low for electrolysis or suggest microbial interference wasn't fully ruled out. Sweetman's team addressed some concerns by sterilizing the chambers with mercury chloride, yet oxygen still formed. Now, with support from UNESCO and £2 million in funding from the Nippon Foundation, Sweetman is launching a 3-year expedition to return to the abyss in 2026. This time, he'll bring custom sensors designed to detect hydrogen, verify geochemical interactions, and determine whether dark oxygen is a local anomaly or part of a global system we've only just begun to see. What we still don't know. Despite centuries of exploration, the deep ocean remains the least understood region of our planet. Scientists often say we know more about the surface of the moon than the abyssal plains beneath our own seas. The discovery of dark oxygen, whether fully confirmed or not, has laid bare just how much mystery still lies beneath. We once believed oxygen was the domain of sunlight and green plants. Now we face the possibility that Earth has always harbored alternate engines, rocks and minerals quietly splitting seawater in the dark, sustaining ecosystems that never needed the sky. If true, this changes the story not just of life's endurance, but of its origin. And yet, time is running out. While scientists prepare instruments and voyages to investigate, industry races ahead to harvest what glitters, often without knowing what it sustains. The question no longer centers on whether Sweetman is right, but whether our curiosity can move faster than our extraction. Beneath miles of crushing sea, Earth may still be whispering the secrets of its first breath. Before we strip the silence for metal, perhaps we should listen. If you believe some mysteries deserve protection, share this video, subscribe for updates from the deep, and let your voice be part of the pause.